Hello, everyone. My name is Jean Paré with Chemco. I'm typically we're the party that have organized this presentation with Carus Chemical. We'll just leave a 1 or 2 minute delay for people to log in. So at let's say 12:02, 12:03, I will start and introduce our speaker and also Ashley from Carus that have helped us put this thing together. So just leaving a few seconds. While people are logging in, I'll just describe a little bit who's Shemco and what's our relationship with Carus. For those who don't know us, Shemco is a chemical company and technology company located out of Quebec, where we typically help qualify and quantify technology for soil and groundwater contaminated sites all across Canada. We typically are involved in about 400 to 500 different sites every year, which ranges from hydrocarbon to chlorinated ethylenes to metals to pesticides. So we're really there to help you find a niche approach when conventional dig and haul or pump and treat technology are not there. Our main focus are really chemical oxidant, chemical reductant, enhanced bioremediation agent, and soil washing technologies. We also have permeable reactive barrier media that can be applied through either reductive or oxidative pathway. So for today, our presenter, Darren and Ashley, are work under the Carus Corporation Company, which is the biggest manufacturer of sodium and potassium permanganate in North America. I won't even might say worldwide, but they have developed through the year, since about 20 years ago, a good understanding of how to apply effectively and what are the impact of applying permanganate in the subsurface aquifer to target specific contaminant of concern. One of the issue that was typically addressed, or we're trying to address with this, is the manganese issue. Some native soil in Canada and elsewhere in the world have very high manganese concentration. So we obviously don't want to create contamination by dosing in the permanganate. And on the flip side, there's a lot of, I'd say, know-how that is coming through 20 years of experience applying this chemistry as a chemical oxidant. So with that, I'll be leaving the floor to Ashley from Carus, which will be introducing our speaker today, which is Darren. Thank you again for attending, and we'll catch you later on with the question time.
All right. Thank you so much, John. I'm going to go ahead and introduce Darren. Darren Scott has worked for Carus for 22 years, with the last year in the Technical Solutions Group. Darren conducts laboratory testing and product demonstrations for Carus municipal, industrial, and environmental customers and prospective new customers. These product demonstrations include technical training, safety presentations, and the installation of safe chemical handling and dosing systems. He is a graduate from Illinois Wesleyan University, Bloomington, Illinois, with a Bachelor of Science degree in chemistry, ACS certified. Mr. Scott is a member of AWWA, Water Environment Federation, and the American Chemical Society. Okay, Darren, I will go ahead and hand the floor over to you.
Thank you, Ashley. So thank you for attending our presentation on manganese in the environment and how the new Canadian drinking water guidelines for manganese are linked to the use of permanganate products for the treatment of solvent-contaminated soils. You see over to the side, you do have a chat box, so if you have questions during the presentation, type into that box, and at the end, we'll answer your question with a question and answer session at the end. We have prepared this presentation to encourage an open discussion of what is known about manganese that results from permanganate ISCO treatment. We have reviewed the information on manganese-in nature, its chemistry, and what is known about the fate of manganese pre and post-ISCO treatment. And we'll go through these topics in the order that you see there on the slide. One of the things we get here at Carus, since we're a permanganate producer, we get many important and interesting questions from our business partners, our customers, and a lot of them have to do with the physical and chemical characteristics of our permanganate family of products. For ISCO treatment, the two products that you'll be familiar with are RemOx-S ISCO reagent and RemOx-L ISCO reagent. Chemically, both of these products are manganese-based because they both include permanganate. The RemOx-S product is a solid product that is potassium permanganate based. The RemOx-L is sodium permanganate based and is applied as a liquid. In the technique of in-situ chemical oxidation, or ISCO for short, RemOx reagents are used to oxidize and remove subsurface chlorinated solvent contamination, typically TCE, PCE, DCE, or components of those. With this treatment, manganese is introduced into the soil of the target treatment zone by the subsurface injection of the permanganate product, whether it be potassium permanganate or sodium permanganate. Given the new manganese drinking water guidelines in Canada, it's important to understand the fate of this manganese in the soil and whether it affects the groundwater in the area. This knowledge will inform treatment best practices for your ISCO sites and the application of permanganate to remove chlorinated solvents. It would seem that based on these new regulations from Canada, there are really three questions that we would want to address when investigating: is there a link between permanganate ISCO treatment and drinking water that is subject to the new Canadian guidelines that are out there for manganese? Our first question would: should we expect that a potable water well with no point of use treatment would be located on or near an ISCO treatment site? So would you have a drinking water well near a site where you're doing active remediation? Our second question: does manganese migrate off a permanganate ISCO treatment site at concentrations greater than the background? And our third question: what is the pre-ISCO concentration of naturally occurring manganese at the site? And does it currently migrate down gradient? So does it already transport off-site even before you've applied permanganate, just from what's naturally in the soil? In May of 2019, Health Canada published new guidelines for manganese in drinking water, setting a maximum acceptable concentration, a MAC, of 120 parts per billion. And this is a health-based guideline. In addition, the guidelines revised and lowered the aesthetic concentration from 50 parts per billion to 20 parts per billion. Aesthetic standards are intended to minimize discoloration, staining, and particulate accumulation in drinking water distribution pipes and storage tanks out in the system. Aesthetic effects are not the same as the health-based guideline, but what they're establishing is that you will see the permanganate or see the manganese coloration at a much lower level than you would at the higher health-based level of 120 parts per billion. These guidelines in Canada are now the lowest global standards when compared to the concentrations targeted by other water agencies. The MAC value is based on recent data of the potential negative health impacts of long-term ingestion of dissolved manganese in drinking water by the vulnerable populations of infants and children. You can see the differences between different parts of the world, with Health Canada at 120, US EPA at 300 parts per billion, the World Health Organization at 400, and then multiple other guidelines. And you can also see the old 50 part per billion in Europe and US EPA for aesthetic, which was what the old Canadian aesthetic guideline was before it was lowered to 20. Also in 2019, the Canadian Council of Ministers of the Environment issued these environmental quality guidelines. These guidelines are specific to manganese-2 ions, the dissolved form of manganese that is bioavailable. What you see is two benchmarks, a short-term and a long-term. The short-term exposure guideline is based on a 48-hour or 96-hour LC50 for 17 different aquatic species. The long-term exposure guideline is based on 14 species of invertebrates, aquatic plants, algae, and fish. The data uses the 10% effect concentration for 10% of exposed species, an EC10. The exposure period was for as little as 7 days for the short-term benchmark and as long as 65 days for the long-term guideline that you see there. And you can see these levels are much higher, 3,600 parts per billion and 430 parts per billion for aquatic life. But keep in mind, this is only for dissolved manganese. So what is known about manganese in the environment? Manganese occurs naturally, and it is the 12th most abundant element in the Earth's crust. So there's quite a bit of it out there. Manganese is generally found in the form of stable oxides, carbonates, and silicates in over 100 different mineral compounds. Pyrolusite, which is also manganese dioxide, MnO2, is the most predominant form of manganese in nature. These minerals are immobile, so they'll stay in place as a solid, but under certain conditions, these solids can erode or dissolve, leading to the detection of low levels of dissolved manganese in drinking water. So what do we know about the background levels of manganese in nature? Well, it's the 12th most abundant element, so we're surrounded by it. In surveys across the US and Canada, manganese concentrations in soil fall into a range of 40 milligrams per kilogram to 900 milligrams per kilogram in the US. Its presence in soil results in vegetable and animal foods containing varying amounts of manganese. Manganese is classified as an essential nutrient and is added to certain foods and nutritional supplements. So you can see it on the back of some of the vitamin pills and supplements you may take. There was one published Canadian soil concentration that had a range of 80 milligrams per kilogram, but could be as high as 7,000 milligrams per kilogram. So what do we expect at an ISCO site based on the chemistry of permanganate? The intent of the permanganate subsurface injection is to react with and mineralize the chlorinated solvent, such as trichloroethylene, under the conditions of the treatment environment. The reaction is shown here. Permanganate represented by MnO4, and then C2HCl3 for the trichloroethane. As permanganate reacts, it mineralizes the trichloroethylene. One thing to keep in mind when we're applying permanganate, there are many different species you see in that equation. The first is the permanganate ion itself, which is the MnO4, which is manganese in the 7+ state. This means the permanganate is soluble in water, and it's also easily traced because it imparts a distinctive pink to purple coloration to the water that it's been applied to. Also, when permanganate is applied in this application, you'll have a highly positive ORP environment. Because permanganate dissolves in water, it is mobile in the subsurface. The other part of this equation, the end product of the reaction, is manganese-4, or typically called manganese dioxide. Manganese dioxide is immobile and remains trapped in the soils of the target treatment zone as a solid. This is exactly what is reported in the literature. In fact, in some cases, there is a concern when applying permanganate that rapid and heavy formation of manganese dioxide will lessen the permeability of the formation of the soil. Many applications might take that into consideration, and there are ways around having that manganese dioxide that may plug up the aquifer. There are applications where they'll add polyphosphates like sodium hexametaphosphate in order to help prevent that plugging of the aquifer when you're applying permanganate. But it'll be site specific whether that's a concern or not, based on the type of soil that you're treating. Finally, it's important to recognize the manganese 2+ ion. Under acidic, reducing conditions, it can be formed when manganese dioxide reacts with material in the soil. Soluble manganese in the 2+ state is soluble in water and therefore is mobile and could move off site. So metals are everywhere in the natural environment and can vary widely in concentration depending on the local geology. Mobilization occurs when metals associated with solid phases are released into aqueous solution. Once in solution, these metals will move with the groundwater or rainwater infiltration. To this point, ISCO treatment sites have broadly studied regulated metals such as arsenic, cadmium, chromium, copper, lead, mercury, nickel, selenium, silver, and zinc. Generally, manganese has not been of interest except to the extent that manganese dioxide can absorb and stabilize other trace metals. They'll absorb onto the manganese dioxide. So there's not a lot of data out there in regards to manganese because it wasn't as big of a concern as these other metals. So can solid manganese compounds dissolve and move off site? In laboratory research conducted by Diana Loomer, this question was investigated by exposing manganese dioxide-coated sand to groundwater containing dissolved organic carbon, DOC, a potential reducing agent. This short-term study concluded multiple things. Manganese release was controlled by a combination of factors: cation exchange, surface complexation, and reductive dissolved reactions. Manganese carbonate solids typically formed via precipitation immediately after release. Small, less than 0.05 milligram per liter concentrations of manganese were released to the groundwater. In his 2001 textbook on permanganate ISCO, Robert Segrist notes that as part of a long-term monitoring program, on ISCO sites manganese levels were evaluated by West following field treatment for the removal of TCE. The soluble groundwater manganese concentrations that were filtered by a 0.45 micron filter were measured over 10 months. The findings included many important things. For permanganate ISCO treatment, there were already background dissolved manganese levels at this site location. The manganese at this site ranged from 0.1 to 0.5 milligrams per liter, which would be above the Canadian MAC level. As anticipated, after they did the injection, very high levels of dissolved manganese were found at the site of the injection whenever permanganate was still present in the sample. So those samples would look pink to purple. And you can see levels between 90 and 5,000 milligrams per liter, but you had active permanganate, so the water was pink. In monitoring wells where the permanganate was fully consumed, those dissolved manganese levels dropped to near or below or just slightly above the normal background levels. So some levels were as low as 0.03, so below the 0.1 to start, and some concentrations were at 3, so slightly above the 0.5 milligrams per liter. From the Department of Defense, the Strategic Environmental Research and Development Program, and the Environmental Security Technology Certification Program, published in a textbook in 2001 that reviewed all ISCO technologies. In that text, the secondary impacts of ISCO were addressed by CREMS, including a review of metals data for 23 different sites. 10 of those sites reported no change in metals concentration above background during and after ISCO. 13 of those sites saw metal concentrations that were elevated above baseline. The metals that typically increased were arsenic, chromium, manganese, and nickel. However, the duration of these increases varied between less than 1 month and greater than 36 months, and were limited to directly in the ISCO treatment zone for all but 2 of the sites. So of those 13, 11 were only right at the injection point, only 2 showed migration. The specific 2 sites that showed down gradient metals increases were both using continuous ozone peroxone sparge applications. In 2001, a master's thesis by Kellyanne Moore evaluated ISCO geochemical parameters by reviewing the water quality data for 30 permanganate ISCO sites. Of specific interest was whether there was long-term impacts on groundwater quality as it related to site and design conditions. The 6-month to 2-year impact on groundwater quality by subsurface oxidant injection was reviewed for the 30 sites, and the analysis determined the following. Geochemical parameters returned to pre-ISCO conditions within this time frame of 6 months to 2 years. Impacts are typically localized to the target treatment zone, so directly where you're doing the application. The most mobility or migration was found in soils that were permeable and homogeneous. At most sites, it took the groundwater more than 1 year to get 30 meters away from the injection site. Manganese concentrations can be predicted by pre and post-ISCO oxidation reduction potential. However, it's highly likely that high ORP after post-treatment typically means you've got permanganate residual, so the solution would also look pink to purple depending on the level. At any ISCO site, it is important to understand what the natural manganese background levels are. Some data has been recorded and included in this thesis presented by Kellyanne Moore. Here are some additional takeaways that she had. Before treatment, the levels of manganese were recorded for these sites. 20 of the sites reported manganese data for 5 distance intervals from the targeted treatment zone, ranging from 3 to 30 meters. and 14 of the sites recorded naturally occurring levels of manganese that exceeded the current Canadian MAC. There's a lot of data here from her thesis, and so we're going to kind of try to summarize it here. The post-treatment or post-permanganate ISCO findings can be categorized into 5 outcomes. 6 of the sites had small persistent increases above the background. A few sites showed large increases post-treatment, but there was no follow-up testing done later. 2 sites showed small short-term increases, and there was no follow-up. Sites reported short-term increases, but returned to background levels, so that was 4 sites. And 4 sites showed decreases or no change between background levels. So 8 of the sites showed no adverse impact. However, special focus could have been placed on the 4 sites with very high residual manganese concentrations. In this case, it's possible, because these were done immediately post-treatment, that the permanganate was still active, and post-treatment of the permanganate could have been applied, could have been too high, or there was still active permanganate that hadn't been consumed with reaction with the chlorinated solvents, where it would have precipitated out as manganese dioxide. In a useful 2019 fact sheet, Health Canada describes permanganate ISCO and offers guidance on its applicability. The fact sheet includes informative summaries that address waste and discharges and long-term considerations following remediation work. In the guidance document assessment, dissolved manganese is typically not an issue, but it should be monitored. It does caution, however, of the potential for the off-site migration of unreacted permanganate. So one thing to keep in mind when doing an ISCO site is how much contaminant is there, what is the soil type, and how much permanganate is to be applied. Health Canada provides the local regulators with a suggestion on evaluating the risk if manganese levels in drinking water exceed the MAC. Magnitude, part of it is above how far above the MAC you are. Marginal short-term exceedances need further evaluation, but may require immediate action. If there's a chronic exceedance slightly above the MAC, that might likely require infants to not consume the formula prepared from tap water. Concentrations of manganese above 0.3 milligrams per liter pose risks to the broader population. In light of this information, are there valuable steps that should be considered when designing a treatment program? There are. You want to review the design conditions at the site. Is there an untreated private drinking water well down gradient of the ISCO site? So something nearby that's being used for drinking water. You also want to evaluate the permeability of the soil media. If necessary, provide a protective reduction barrier down gradient of the injection point. And then always there's a cost consideration, but you want to optimize the mass of permanganate injected at the site so you're not overfeeding permanganate above what you need to do your remediation. So to conclude, let's revisit the 3 fundamental questions that we started with. Question 1, What is the likelihood that an untreated potable water well would be located on or down gradient of an ISCO remediation site? Very highly unlikely, because of the chlorinated solvent being present, that there would be a drinking water well nearby. So highly unlikely. And you could control it if there was one nearby. Question number 2. How likely is it that soluble manganese will migrate off the target treatment zone and be detected in an untreated drinking water well at levels greater than 0.12 milligrams per liter? And could this even be correlated to the treatment at the site? It's potentially possible, but will be dependent on the soil geology in the area, the physical chemical characteristics of the soil, the combination of treatment techniques and treatment levels used, and are there any migration barriers that are going to be installed at the site to prevent this? Question 3, what is the pre-ISCO concentration of manganese at the site, and is it migrating down gradient? Well, because manganese is ubiquitous in the environment, the groundwater at many ISCO sites can exhibit natural manganese concentrations higher than the current Canadian MAC before treatment even begins. There isn't any real data on down gradient migration for this. At this point, we'll pass it back to Jean-Pierre to see if there's any questions that we can answer or further discussion.
Okay, thanks, Darren. Jean, are you there still? Okay, it looks like we don't have any questions that came in, but if you do, if anyone in the audience that does have a question, feel free to reach out to both. Oh, it looks like one just came in, Darren.
Okay.
What is the threshold MnO4 to see pink color?
So with the naked eye, you can see down to roughly somewhere between 0.3 and 0.5 milligrams per liter of permanganate. So we have a lot of customers that use permanganate for ISCO, and at their monitoring wells, they'll do 2 ways. They can actually grab samples and they can put it in a white styrofoam coffee cup and see that low level of 0.3 to 0.5, so it kind of appears. And then there's also field monitoring equipment with spectrophotometers where you can measure the level. Typically, they only use those when they're at much higher levels, so they've immediately done an injection and want to see how much permanganate's at the actual injection point. And there they might be injecting, 1% solution, so 10,000 parts. And so they want to get a measurement of how much they applied. And then sometimes they'll measure that a week or 2 weeks downstream to see how high the level is, so that it dropped from 10,000 parts per million down to 1,000 parts per million in those monitoring wells.
Okay, great. Thanks, Darren. And I think that concludes the questions for today. If anyone does have additional, feel free to reach out to both. Oh, another one. Sorry, Darren. I'm going to give you this one too. Is there any perspective on using ISCO-ISCR combination in regards to this issue?
So they're talking about permanganate
From the same
treatment.
question. Yep.
Yeah. So doing ISCO and then following it up with reductive. So if you're going to apply something that can cause a reducing environment immediately after applying permanganate, reducing conditions can resolubilize, but it's going to be based on the site conditions and how much you're applying. You could possibly resolubilize some of that manganese dioxide into the groundwater. So it would be a concern if you applied them one right after the other. But it's going to be based on how much you're applying, what the soil type is, kind of all those applications. So.
Okay, great. Thanks, Darren. Thanks, Jean-Pierre, for attending and helping us with this webinar. And thanks to all our attendees. Have a great day.